We're going to be exploring cutting-edge research,
Absolutely.
tackling some mind-bending concepts,
Oh, yeah.
and maybe even rewrite what you thought you knew about the nature of reality.
You know what's fascinating about antimatter?
What's that?
Is that it's not just a science fiction concept.
No.
It's a real substance
Huh.
made up of antiparticles, which
Wow.
are essentially the mirror images of the particles that make up everything around us.
Okay, so antiparticles are like the evil twins of regular particles.
Yes.
Same mass, but opposite charges.
Exactly.
But it's not just about being opposites, right?
Right.
When matter and antimatter meet, they annihilate each other,
They do.
releasing a huge burst of energy.
That's right. And this leads to one of the biggest mysteries in cosmology, the Baryon asymmetry problem.
Okay.
The Big Bang should have created equal amounts of matter and antimatter,
Right.
which would have annihilated each other, leaving nothing but energy. Yet here we are,
Yeah.
in a universe made almost entirely of matter.
So where did all the antimatter go?
Well, that's the big question, isn't it?
That's what we're trying to figure out today.
Yep.
And one of the key places scientists are looking for answers is at CERN,
Absolutely.
the European Organization for Nuclear Research, home to the famous Large Hadron Collider.
Right. CERN's antiproton decelerator, or AD, is a crucial tool for studying antimatter.
Okay.
They're able to create antiprotons, slow them down, and even use them to create antihydrogen atoms.
Antihydrogen.
Yeah.
So that's like the antimatter version.
Exactly.
The most basic element in the universe.
The simplest atom.
What's so important about studying antihydrogen?
It's all about looking for subtle differences between matter and antimatter.
Okay.
Even the tiniest discrepancy could have profound implications for understanding why matter won out in the early universe.
Okay, I'm starting to see why this is such a big deal.
Yeah.
But wouldn't any antimatter created in a lab just instantly annihilate with the surrounding matter?
You would think so, right?
How do they even study it without everything exploding?
Well, it's a delicate process.
Okay.
They use magnetic fields to create a sort of trap
Uh-huh.
that suspends the antihydrogen atoms in a vacuum, preventing them from coming into contact with regular matter.
So they've essentially built a container for something that wants to destroy everything it touches.
That's a good way to put it, yeah.
That's some seriously impressive science.
It is, and it's allowing them to do some incredible experiments.
Like what?
For example, for a while there was a theory that antimatter might have repulsive anti-gravity.
Wait, so antimatter might have fallen up instead of down?
That's the idea.
That would turn our understanding of gravity on its head.
It would have been a revolution in physics.
Yeah.
But recent experiments at CERN, specifically one called LHAG, have put that theory to rest.
Oh, okay.
They've shown that antihydrogen falls at the same rate as regular hydrogen.
So antimatter obeys gravity just like everything else.
It seems so.
Does that mean those experiments were a failure?
Not at all, even though it seems like a negative result.
Okay.
It's actually a huge step forward. It rules out certain theories and helps us narrow down the possibilities for why the universe is the way it is.
I guess science is full of surprises.
It certainly is.
What other fascinating things have they learned from trapping antihydrogen at CERN?
Well, there's another experiment at CERN called Asymmetry that's been making headlines.
Okay.
They're looking at something called the hyperfine structure of antihydrogen.
Okay, hyperfine structure sounds a bit technical.
It is.
Can you break that down for me?
Essentially, it refers to tiny energy differences within an atom.
Uh-huh.
By comparing the hyperfine structure of antihydrogen to that of regular hydrogen.
Okay.
They're looking for any discrepancies, no matter how small.
So it's another way of looking for subtle differences between matter and its evil twin.
Precisely any difference.
Mm.
Even the tiniest one could have huge implications.
Wow.
It could point to new physics beyond what we currently understand
Okay.
and give us clues about the nature of antimatter itself.
So the research at CERN is giving us a really detailed look at antimatter.
It is.
But we also touched on the idea that antimatter might exist out in the cosmos, not just in labs.
That's right. One place we see evidence of antimatter is in cosmic rays,
Okay.
which are high-energy particles that bombard Earth from space.
Right.
A small fraction of them are actually antimatter particles, like positrons.
Hold on. So antimatter is raining down on us from space?
In very small amounts, yes.
Should I be worried?
No need to panic. The amount of antimatter in cosmic rays is tiny,
Okay.
and most of it is annihilated before it reaches the Earth's surface.
Okay, that's a relief. But where are these cosmic rays coming from?
That's a big question.
Yeah.
Some might be produced in extreme environments like black holes or supernovae,
Okay.
where the energy levels are high enough to create matter-antimatter pairs?
So these cosmic events are like giant particle accelerators churning out antimatter.
In a way, yes.
Pretty wild.
It is, and it gets even wilder. Some scientists speculate that there might be entire antimatter galaxies out there in the universe.
Antimatter galaxies, that sounds like something straight out of science fiction.
I know, right?
Are there any signs that they might actually exist?
No definitive proof yet,
Okay.
but there are some theoretical possibilities and observational anomalies that keep the idea alive.
Okay, I'm hooked. We have to talk more about antimatter galaxies.
We will.
And the theoretical explanations for why our universe is dominated by matter, but I think that's a good place to pause for now.
All right.
We've covered a lot of ground already,
We have?
and we'll delve deeper into these mysteries in the next part of our deep dive.
Sounds good.
Welcome back to our deep dive into the world of antimatter. Before the break, we were just starting to touch on the mind-boggling idea of antimatter galaxies and some of the theoretical frameworks that attempt to explain the dominance of matter in our universe.
Yeah, it's true. Even with all the incredible research being done at places like CERN, there's still so much we don't know. The existence of antimatter galaxies is a tantalizing possibility, even if we haven't directly observed them yet.
I have to admit, the idea that there could be entire galaxies out there made of antimatter is just, what's a lot to process. I mean, wouldn't they look pretty similar to regular galaxies if we observed them? How could we even tell the difference?
You're right. Light from an antimatter galaxy would look very much like light from a regular galaxy.
Okay.
That's why detecting them would be so challenging.
Right.
One potential way would be to look for the telltale signs of matter-antimatter annihilation.
Oh, right. We talked about how matter and antimatter annihilate each other, releasing a huge burst of energy. So would we be looking for massive explosions or something?
Exactly. If an antimatter galaxy were to collide with a regular galaxy, or even if their outer edges brushed against each other, the resulting annihilation would release a tremendous amount of energy in the form of gamma rays.
So we're essentially looking for giant cosmic fireworks displays. Sign me up for that research team, but have we actually observed any gamma ray bursts that could be explained by this kind of annihilation?
There have been some unexplained gamma ray bursts detected over the years that could potentially fit the bill. However, attributing them to matter-antimatter galaxy interactions is still very much in the realm of speculation.
Basically.
More research is needed to definitively link these bursts to antimatter annihilation.
It seems like the idea of antimatter galaxies is still highly theoretical. Are there any other observational clues or theoretical frameworks that support their existence?
One theoretical idea involves the very beginning of the universe,
Okay.
the Big Bang.
Right.
Remember the matter-antimatter asymmetry problem we discussed?
Yeah.
Well, some theories suggest that this asymmetry might not have been perfectly uniform throughout the entire early universe.
So instead of a perfectly even split of matter and antimatter at the Big Bang, there might have been regions where matter slightly dominated and other regions where antimatter slightly dominated.
That's the idea. As the universe expanded and cooled, these regions could have evolved into separate domains.
Okay.
Some made mostly of matter and others made mostly of antimatter. And those antimatter-dominated regions could have eventually formed antimatter galaxies.
That's incredible. It would be like looking into a mirror universe where everything is made of antimatter. But how could such separate domains even form in the first place? Wouldn't they have just annihilated each other at the boundaries?
That's a great question, and it's one of the challenges for this theory. It would require some mechanism to keep those domains separate during the early universe,
Right.
allowing them to evolve independently.
Okay, so the idea of antimatter galaxies is still pretty speculative, but it's definitely a fascinating concept to consider. It really highlights how much we still don't know about the universe and the stuff it's made of.
Absolutely, and this is where the theoretical side of antimatter research really comes into play.
Right.
While experiments like those at CERN are vital, we also need theoretical physicists to develop models and frameworks that help us interpret those results and make predictions about what we might find out there in the universe.
Right. We touched on the idea of CP violation earlier, but I have to confess I'm still a bit fuzzy on how that concept helps explain the matter-antimatter asymmetry. Could you walk me through it again?
Of course, CP violation or charge parity violation essentially means that the laws of physics are not perfectly symmetrical when it comes to matter and antimatter. There are subtle differences in how they behave in certain interactions.
So it's like having a set of rules that apply slightly differently depending on whether you're dealing with matter or antimatter.
That's a good way to put it. And even those tiny differences at the level of subatomic particles could have had a huge impact on the evolution of the early universe.
But wouldn't those differences just result in a slightly uneven split between matter and antimatter? Wouldn't most of it still annihilate, leaving a universe with very little of either?
You're right. CP violation alone isn't enough to explain the amount of matter we see today. We need additional mechanisms to amplify that initial imbalance.
Okay.
And that's where the concept of baryogenesis comes in.
Ah, periogenesis. It's like the cosmic process that tips the scales dramatically in favor of matter. Can you tell me more about how that might have worked?
Baryogenesis is a catch-all term for any process that could have created an excess of baryons, the particles that make up protons and neutrons, over antibaryons in the early universe.
So we're not just talking about a slight tilt in the odds. We're talking about processes that actively generate more matter than antimatter.
Exactly. There are several proposed mechanisms for baryogenesis, each with its own set of conditions and implications.
Could you give me an example of one of these mechanisms?
Sure, one idea involves a concept called spontaneous symmetry breaking. Imagine a perfectly symmetrical ball balanced on top of a hill. The ball represents the early universe in a symmetrical state. If the ball rolls down the hill, it breaks the symmetry, choosing a specific direction and ending up in a less symmetrical state at the bottom.
Okay, I think I'm following. So how does this relate to baryogenesis?
Some theories suggest that the early universe might have undergone a similar process of spontaneous symmetry breaking,
Okay.
transitioning from a state of perfect symmetry between matter and antimatter to a state where matter slightly dominates.
So the universe rolled down the hill and ended up in a state where matter won out over antimatter.
That's a great analogy.
Ah.
And this symmetry breaking could have been driven by new undiscovered particles or forces that existed only in the extremely high energy conditions of the early universe.
This is all fascinating, but I have to admit it's getting pretty complex.
Sure.
Are there any guiding principles or conditions that help physicists narrow down the possibilities for baryogenesis?
There are. One of the most important frameworks is something called the Sakharov conditions, named after the Russian physicist Andrei Sakharov.
Right.
He aligned 3 conditions that must be met for baryogenesis to occur.
3 conditions. That sounds promising.
Yeah.
What are they?
First, there must be a process that violates baryon number conservation.
Okay.
In other words, there needs to be a way to create more baryons than antibaryons tilting the scales.
So something that goes beyond just the slight imbalance created by CP violation.
Exactly. Second, we still need that CP violation we talked about earlier. This ensures that matter and antimatter are treated slightly differently, so any excess of baryons doesn't get instantly wiped out.
Okay. So we need a way to make more baryons and a way to make sure they stick around. What's the third condition?
The third condition is that the universe must have been out of thermal equilibrium at some point.
Okay.
This means that there were periods of imbalance and instability where those baryon-creating processes could really take hold and have a lasting effect.
So like a brief moment of cosmic chaos that allowed matter to gain a foothold.
The Sakharov conditions give us a really valuable framework for thinking about baryogenesis and help guide theoretical physicists as they develop new models.
This is all pretty mind-bending stuff. We've talked about antimatter in labs, antimatter raining down on us from space, the possibility of entire antimatter galaxies, and these incredibly complex theoretical frameworks for explaining the matter-antimatter asymmetry. I feel like we've barely scratched the surface.
You're absolutely right. It's a vast and complex field, but it's one that's constantly evolving as new discoveries are made and new theories are proposed.
Well, I'm definitely eager to hear more. What other intriguing avenues of antimatter research are out there? I feel like we've only just begun our journey.
I agree, and there are some particularly exciting experiments happening right now that could have huge implications for our understanding of antimatter. Why don't we take a short break and come back to discuss them in our final segment?
Welcome back to our deep dive on antimatter. I feel like we've traveled to the very edge of the universe and back, and we're still left with more questions than answers.
That's the beauty of scientific exploration, isn't it? Each discovery opens up new avenues of inquiry, leading us deeper into the mysteries of the cosmos.
Before the break, you mentioned some exciting experiments that could revolutionize our understanding of antimatter. I'm all ears. What's on the horizon?
Well, at CERN, they're constantly pushing the boundaries of what's possible. One experiment that I find particularly fascinating is called GBR.
GBR, I don't think we've touched on that one yet. What's so special about it?
GBR is designed to measure how antimatter responds to gravity. It's like a modern-day version of Galileo's famous experiment, but instead of dropping objects from the Leaning Tower of Pisa, They're going to be dropping antihydrogen atoms.
Wait, they're going to literally drop antimatter and see if it falls at the same rate as regular matter. Isn't that incredibly difficult and maybe a tiny bit dangerous?
It's definitely a challenging experiment. They need to create and trap antihydrogen atoms, then release them in a controlled way within a specialized chamber where they can precisely measure their descent. But the potential payoff is huge.
Okay, I'm seeing the appeal. What could we learn from watching antimatter fall? Didn't we already establish that antimatter obeys gravity?
We did, thanks to the ALPHAG experiment. But GBR aims to take those measurements to a whole new level of precision. It could confirm or refute the weak equivalence principle with unprecedented accuracy.
The weak equivalence principle. Remind me what that is again.
The weak equivalence principle states that all objects, regardless of their mass or composition, fall at the same rate in a gravitational field. It's one of the cornerstones of Einstein's theory of general relativity.
Ah, so it's about testing one of the most fundamental laws of physics. But with antimatter, this time I'm starting to see why this experiment is such a big deal.
Exactly. If G-bar finds even the slightest deviation from the weak equivalence principle, it would have profound implications for our understanding of gravity and the relationship between matter and antimatter.
That's incredible. So CERN is continuing to be at the forefront of antimatter research. But I imagine there are other exciting developments happening elsewhere as well.
Absolutely. New facilities dedicated to antimatter research are being built around the world, and international collaborations are fostering innovation in this field. It really does feel like a golden age for exploring this fundamental aspect of our universe.
It's exciting to think that we might be on the cusp of some major breakthroughs. But it's not just about the experiments, right? We need the theoretical frameworks to make sense of all this data.
You're right. Theoretical physicists are hard at work developing new models and exploring concepts that could explain the matter-antimatter asymmetry and the nature of antimatter itself.
We've talked about CP violation and baryogenesis, but are there any other theoretical avenues that scientists are exploring?
Oh, there are plenty. Some researchers are delving into the world of supersymmetry, which proposes the existence of partner particles for every known particle in the standard model. Others are exploring grand unified theories which attempt to merge the fundamental forces of nature into a single framework. And then there's string theory, which proposes that the universe is made up of tiny vibrating strings.
Wow, those are some pretty mind-boggling ideas. It sounds like theoretical physics is getting pretty wild. But how do these theories actually help us understand antimatter?
Well, for example, some supersymmetric theories predict the existence of new particles that could have played a role in baryogenesis, providing a mechanism for creating the matter-antimatter asymmetry.
So these theories could offer new pathways to solving the big mystery of why our universe is made of matter.
Exactly. And what's so exciting is that there's a constant back and forth between theory and experiment. New experimental results challenge existing theories, and new theoretical ideas inspire new experiments. It's a dynamic process that drives scientific progress.
It feels like we're on the verge of something truly revolutionary. But as we wrap up this deep dive, I think it's important to acknowledge that despite all the amazing progress, the ultimate puzzle remains unsolved. Why is there something rather than nothing? Why is our universe made of matter?
You've hit on the big questions, the ones that have captivated philosophers and scientists for centuries. And while we may not have definitive answers yet, the pursuit of those answers is what drives us forward.
It's a journey of exploration and discovery, and it's a privilege to be a part of it. Even without all the answers, I feel like I've gained a deeper appreciation for the incredible complexity and beauty of the universe.
I agree. And that's what I hope you'll take away from this deep dive. While the search for answers continues, the very act of questioning, exploring, and marveling at the wonders of the universe is a deeply rewarding experience in itself.
Well said. I think that's a perfect note to end on. Thanks for joining me on this incredible journey into the world of antimatter.
It's been my pleasure. Until next time, keep exploring, keep questioning, and never stop being curious about the universe and all its mysteries.